apologies. I've managed to pick up a cold in the last couple of days, so apologies for my voice sounding a bit nasally. But I'll be talking to you about scale invariant R-squared inflation. I also work with his work completed with Karsten Vanderbroek, same supervisor as Elsia, what we just heard. So basically, just because I know there's a couple of talks about inflation after me, I'm just going to go through some basic motivation of inflation. So firstly, what is inflation? And Alan Guth gave a very nice way of describing this, and he said inflation is the bang of the Big Bang. Basically, he meant it's an accelerated expansion in the early universe. Okay, great. So how does this work? Now, it's actually quite simple mechanism. It's something you can do on, it's like a famous back of the envelope sort of calculation. I mean, you can just look at it in terms of a Hubble parameter, for instance. So we take our expansion rate, what we all know, so A dot over A equals H, and we say, okay, let's make H constant. I mean, from high school mathematics, you can solve this quite easily, and you find that we have an exponential growth. Perfect, exactly what we wanted. So when we're talking about inflation, it makes sense to also define a new time variable, the E-fold number, which is just the log of A. So now we say H is a constant, great, wonderful. So what does that actually mean? So if we just take our standard flat FRW background, we have some scalar field, so we have our normal Freeman equations, our acceleration equations, and a Lagrangian with just some scalar field in it. And we're going to say, okay, so from this, we can obviously work out all the equations of motion and the stress energy tensor, define rho and P. We can then obviously work out our Freeman equation and our acceleration equation in terms of our scalar field. Now, what does this actually mean? Clearly, if we say we want H to be a constant and we want the acceleration to be growing, we need our potential to be much greater than phi dot squared. We need our potential to be greater than 0, and we need it to be really, really flat. These are just our slow roll conditions. And more formally, I mean, we actually write these in some terms of some parameters. So while these parameters, so we've got epsilon and eta here, which is just basically the relative, it's the, well, it's defined as such, just the differential of our potential and the second differential of our potential. And as long as these are held, we can say we're in some sort of inflationary epoch. So what does this mean? Essentially, this means we'll be on some sort of plateau. And this gives rise to what's called like a quasi-de Sitter behavior. And ideally, what we're saying is, while we're on this plateau and we fulfill these slow roll parameters, we have inflation, everything's great. And once inflation ends and we end up in, and the scalar field starts to speed up, we want to be going towards some sort of reheating or preheating phase. Now, I'm not going to be focusing on that in this talk, but I have done some work on that. Maybe we'll have questions for that afterwards. Also, so quickly, just motivation for this, why inflation? So we know what inflation is, it works nice. So why do we care about the blue curve and not that red curve on the graph there? Essentially, there's a lot of problems with just having a standard Big Bang theory, where you have the flatness problem, which I'll go into in a little bit more, this horizon problem, which is just causality of when you look up at the sky and you can take two patches of sky, they've never actually been in causal contact, formation of galaxies, and there's many more problems that sort of come with this. So just to illustrate how inflation helps these, we can just take the Freeman equation. I've made it slightly more simplified here, and I've written it in terms of just the density parameter as well. And we say, okay, right, we have a density parameter. And now we know we go through several epochs. Let's just say we have inflation, matter, and radiation. Let's keep everything very simple. And we say, okay, great. Now we measure the flatness of the universe, this density parameter, to be very close to 0, like 10 to the minus 2. And so we see, obviously, if we're in a radiation or matter-dominated epoch, it's actually an unstable fixed point. Whereas if we're in inflation, it becomes stable, and actually this parameter wants to go to 0. So hopefully that convinces you of inflation. Now, I'm going to be talking to you about a modified theory, but before I get there, we'll sort of brief you into it, and we'll talk about Starobinsky's inflation. So I've just written down the generic action there. It's for a r plus r squared, and mu is just a inverse of mass, that can be determined at a later point. And then we can change the Einstein frame. This is just done through a conformal transformation. This can be looked up in any sort of GR textbook, Wald, Carroll, whatever, what name your favorite one. And what I've done is I've basically, after what I've just talked to you about inflation, hopefully you're convinced that it's the potential that we're actually looking at. So if we just say phi is 0, and we're not worried about the other scalar field, but we look at just this psi field that I've now got that came from r squared, we can already see just here how we naturally have just a very nice plateau that then drops, and we can have some sort of reheating or preheating effect around 0. And that's just from the most simplest sort of higher order term you can think of in an F of R theory. So with that being the case, I just want to move on to my model. Now, my model obviously looks slightly more complicated than just a standard Stravinsky case. And I mean, we still have our R squared, but we also have a coupling of a scalar field to the Ricci scalar. Plus, we have our potential that has a Higgs-like form there. Now, we initially did look at making this sigma a constant, but if we allow sigma just to vary as another field, it gives rise to some interesting features that I want to sort of talk about. So as I say, also another key point to mention in here is there's no explicit mass scale. And so a nice part of this model is that we can actually sort of determine a fundamental way of choosing the Planck mass. So at the bottom there, I've just written the field in the Einstein frame. It just makes it easier to analyze in the Einstein frame because then we can just look at the potential and see what's happening. It's just a bit easier to visualize. So this model benefits from this scale invariant Weyl transformation in the Einstein frame. So it's just given by the terms there. And so with a symmetry present, we can obviously we can use Noether's current. And we can just basically simplify this down to a two-field problem if we're going to include sigma to also be dynamical. So with that being the case, you can see on the right here, you can then plot it into a three-dimensional plot. And this blue line here sort of indicates the trajectory of the fields, how they behave. And you can sort of see how there is a nice plateau that they want to fall down on. And then there's this Higgs potential sort of well that they will then fall down at a later point. Now, obviously, as is the case, the symmetry is spontaneously broken when the fields reach their potential, when they reach the minimum of their potential, and they settle at their vacuum expectation values. So in this case, there should also be a sigma here, but basically what you'll find is clearly chi squared will equal sigma squared, and then you can determine from the other potential the ratio here. And what we actually see is that our mass scale that we introduced is actually just determined by some parameters of the model and the ratio of our vacuum expectation values. So depending on your initial conditions and your parameter set, you can actually have a natural way of determining a fundamental mass scale, which we will just obviously interpret it as the Planck mass.
2 minutes.
Thank you. So what we want to then do is we can then numerically integrate to find the equations of motion, see what the dynamics look like, see what's actually happening in our behaviors. Now, I'm not going to write down all the equations and all the perturbations and everything else. I'm just going to show you the plots just because we haven't got that much time. So basically up here, you can sort of see what actually happens. Sorry there. And you can sort of see there's two periods of inflation. And one period is just where we would have effective two-field, the two-field model, like a Stravinsky type, and that's just up to about 65 e-folds here. And then you have where sigma then plays a role, and you see it quickly cuts off and ends inflation. So then we can look at the perturbations. Now here's the actual interesting part. So I haven't gone through all the perturbations and all the, like you want to look at the spectral index and the tensor to scalar ratio. They are all fine. It's just, there's some interesting points here and I'll obviously push for time a little bit. So what we actually see when we calculate the power spectrum is we have a rapid drop in power at large and small scales. Now this is actually completely due to allowing sigma to vary dynamically. If it was just constant, we would have a very nice Stavinsky and everything would look very fine. And we'd have just perfect inflation almost. A little bit boring, but it'd be great. What we have now is, you can parameterize and you say, well, I need it to be in, say, 10 to the minus 2 to 10 to the 2. I need it to be flat, and that's fine. You can choose your parameters as such. And then, but at larger wavelengths, let's say 10 to the 6, wavelength modes at 10 to the 6, what you would have there is you have a drop in power. Now, what this means is in this model, just this model, you're going to be predicting against primordial black holes. You're not going to have that big jump that you'd want to see, for instance, at least not in the mechanism coming from inflation. So in the bottom graph there is just to show you how this model sort of fits to lambda CDM. And we see obviously it's at low multiples that we actually have a larger discrepancy, but that's to be sort of expected. So just because of my time, I'll just leave the conclusions up, but basically briefly went through slow roll inflation, Stavinsky model, then extended to my model, and hopefully you found the non-trivial features interesting as well. So I'll take any questions if you have any.
Cool. Thank you very much. Okay, any quick questions? Okay, I think in the interest of time, we should move on. Thank you very much.